Hello everyone. We're going to discuss about the factors affecting fluorescence. Fluorescence intensity. There is one nature of the molecule, nature of the substituent, effect of concentration, absorption, oxygen, pH, temperature and viscosity, quantum yield, intensity of incident light, path length, photo decomposition, quenches and scatters. We all know that not all molecules can show the phenomena of fluorescence and phosphorescence. The reason is that those molecules which absorb, only those molecules that absorb within the UV or visible radiation are the only molecules capable of showing fluorescence or phosphorescence. Because from the ground state, the molecule will go to the excited state only when they absorb sufficient radiations, which are present either in the UV region, UV radiation or visible radiation. Those, so now only those molecules can undergo fluorescence. The greater the absorbency of the molecule, the more intense the luminescence. That means the more intense the light that is to be emitted. That affect the fluorescence is the type of group substituent in the molecule. Electron donating group enhances fluorescence, e.g. the amino group, the hydroxy group, and so on. While the electron withdrawing group decreases or destroys fluorescence is the carboxylic, the nitro group, or the azo group, and so many of them. Generally, aromatic compounds with low energy show this type of effect. The concentration also affects the fluorescence. The fluorescence intensity is directly proportional to the concentration of subcutaneous substance only when the absorbance is less than 0.2. And you can calculate the fluorescence, the concentration using this formula, A equals to AB, ABC, while or A equals to log I naught divided by IT, where I naught is intensity of incident light, IT is intensity of transmitted light, A is absorbance, B is path length, and C is concentration. Absorption. This method is very sensitive. So the absorption of fluorescent substance on the container will create serious problems. So strong or concentrated solution must be diluted. This leads to decrease in the fluorescence. Intensity of incident light. Increase in the intensity of incident light on the sample. The fluorescence intensity also increases. Oxygen. Um, the presence of oxygen may interfere in two ways. By direct oxidation of the fluorescent substances to non-fluorescents, or by quenching of the fluorescence, as in by killing it completely. Now, the paramagnetic substance like dissolved oxygen and many transition metals with unpaired electrons dramatically decreases fluorescence and causes interference in fluorimetric determinations. The paramagnetic nature of molecular oxygen promotes intersystem crossing from singlet to triplet state in other molecules. The longer lifetime of the triplet state increases, the opportunity for radiation less the activation to occur. pH. Alteration of the pH of a solution will have significant effect on fluorescence. For example, aniline in alkaline medium gives visible fluorescence, but in acidic condition gives fluorescence in the ultraviolet region. Now, relatively small changes in the pH can sometimes cause substantial changes in the fluorescence intensity and spectral characteristics of the fluorescence. For example, serotonin shows a shift in fluorescence emission maximum from 330 nanometer at neutral at neutral pH to 550 nanometer in strong acid without any change in the absorption spectrum. In the molecules containing acidic or basic functional groups, the changes in pH of the medium change the degree of ionization of the functional groups. This in turn may affect the extent of conjugation or aromaticity of the molecule, which affects its fluorescence. Like the example I give is the aniline in acid and in base. Now, let me give another this example. You see, in aniline, the aniline shows fluorescence while in acid solution, right? So it does not show fluorescence due to formation of anilinium ion. Therefore, pH control is essential while working with the molecules, with such molecules, and suitable buffers should be employed for the purpose. Intensity. A rise in temperature is always accompanied by a decrease in fluorescence. The change in temperature causes the viscosity of the medium to change, which in turn changes the number of collision of the molecules of the fluorophore with solvent molecules. Besides solvent polarity, a change in the polarity or hydrogen bonding ability of the solvent may also significantly affect the fluorescent behavior of the analyte. The difference in the effect of the solvent on the fluorescence is attributed to the difference in their ability to stabilize the ground and excited states of the fluorescent molecules. Beside solvent polarity, solvent viscosity and solvents with heavy atoms also affect fluorescence and phosphorescence. If viscosity of solution is more than the frequency of collision is more, if the viscosity of the solution is more, the frequency of the collision are reduced and intense increases an increase in fluorescence intensity, and it increases the fluorescence intensity. Now, increased viscosity increases fluorescence as the activation due to collisions is lowered. A higher fluorescence is observed when the solvents do not contain heavy atoms, while phosphorescence increases due to the presence of heavy atoms in the solvent. Fluorescence. This is calculated as number of photon emitted divided by number of photon absorbed. It is always less than 1.0 since some energy is lost by radiation in less pathways, e.g. collisional, intersystem crossing, vibrational relaxation. Increase in intensity of the incident light on the sample increases fluorescence intensity, and this intensity of light depends on the light emitted from the lamp, the excitation monochromatus, and the excitation slit width. The effect of path length depends on both the excitation and emission slit width. Use of the microcuvette does not reduce the fluorescence, while the microcells may reduce interference and increases the measured fluorescence. When the molecule absorbs intense radiation, the fluorescent substance photochemical decomposition occur whereby the fluorescent substance become non-fluorescent, meaning it kills the fluorescent substance. Is in fluorescence is when there is decrease in fluorescence intensity due to specific effect of the constituent of the solution. This could be due to concentration, pH, pressure of the chemical substance, viscosity, temperature. All those factors that affect can cause quenching, can destroy or decreases the fluorescence intensity. There are four types of quenching: self-quenching, chemical quenching, static, Quenching and collision quenching. Self-quenching or concentration quenching. At low concentration, it is observed that the same substance increases in a fluorescence is observed at high concentration, whereby at low concentration there is a low fluorescence. The intensity of the fluorescence reduces. Chemical Chemical quenching is a process whereby the fluorescent intensity decreases due to factors like pH, presence of oxygen, halide, and heavy metal. For instance, pH, aniline at pH 5 to 13 gives fluorescence, but at less than 5 or greater than 13, it does not even exhibit any fluorescence. Likewise, halide like chloride, bromide, iodine, and electron withdrawing group leads to quenching of the fluorescence. Heavy metals as well leads to quenching because of the collision of triplet ground state. Static quenching. This occurs due to complex formation. For instance, caffeine reduces the fluorescence of riboflavin by complex formation. Collision quenching. It reduces fluorescence by collision, where number of collisions increase, hence quenching takes place. Scattering of the incident light after passing through the sour sample leads to decrease in fluorescence intensity. This could be due to is mainly due to the colloidal particles in the solution. Thank you for watching. Don't forget to subscribe.